Before Galileo Galilei was born in 1564, Europe lived under a world that had remained largely unchanged for nearly 1,500 years. This world was shaped by tradition, authority, and faith, rather than experimentation and observation. Knowledge about nature, the universe, and humanity's place within it was not something to be questioned freely. Instead, it was inherited from ancient thinkers and firmly supported by the Catholic Church, which stood as the most powerful intellectual and spiritual authority of the time. To understand why Galileo's ideas were so revolutionary, it is essential to understand the world that existed before him and how deeply church-backed science dominated human thought. For centuries, European knowledge of the natural world was based primarily on the works of ancient Greek philosophers, especially Aristotle and Claudius Ptolemy. Aristotle's ideas about physics, motion, and the structure of the universe were treated almost as unquestionable truths. He taught that the universe was orderly, purposeful, and divided into two distinct realms: the imperfect earth below the moon and the perfect, unchanging heavens above it. According to this view, earth was heavy and flawed, while the heavens were eternal and flawless. These ideas shaped how people understood everything from falling objects to the movement of stars. Ptolemy, a Greek astronomer living in the 2nd century, built upon this philosophical foundation by developing a detailed model of the universe. In his system, Earth stood motionless at the center, while the sun, moon, planets, and stars moved around it in complex circular paths. This Earth-centered or geocentric model explained the apparent motion of heavenly bodies well enough to predict eclipses and planetary movements. Because it seemed to match everyday human experience after all, Earth feels still, Ptolemy's model was widely accepted. When Christianity spread across Europe and became deeply rooted in society, church scholars adopted these ancient ideas and integrated them into religious teachings. The geocentric universe aligned comfortably with certain interpretations of the Bible, which spoke of a fixed earth and a moving sun. As a result, Aristotle's physics and Ptolemy's astronomy were not just scientific theories. They became part of a sacred worldview. To challenge them was often seen as challenging religious truth itself. During the Middle Ages, education was controlled almost entirely by the Church. Universities, libraries, and centers of learning were connected to religious institutions. Scholars studied theology above all else, and natural philosophy. What we now call science was expected to support religious beliefs, not contradict them. Learning relied heavily on studying ancient texts, rather than conducting experiments. Students memorized and commented on the works of Aristotle, instead of testing his ideas against real-world evidence. Truth was something handed down by authority, not discovered through questioning. This reliance on authority created a culture where doubt was discouraged. Asking too many questions about nature could be seen as arrogance or even heresy. The Church feared that questioning accepted knowledge might lead people to question religious doctrines, moral rules, and the authority of religious leaders. As a result, intellectual freedom was limited, and new ideas spread slowly, if at all. The idea of motion provides a clear example of how restrictive this world-view was. Aristotle taught that heavier objects fall faster than lighter ones, and that an object in motion must be continuously pushed to keep moving. These ideas went largely unchallenged for centuries because scholars trusted Aristotle's authority rather than testing his claims. Everyday observations that contradicted these ideas were often ignored or explained away. Astronomy followed a similar pattern. When astronomers noticed that planets sometimes appeared to move backward in the sky, instead of questioning the Earth-centered model, they added more complex mathematical adjustments to preserve it. The goal was not to find the simplest or truest explanation, but to protect the established system. This showed how deeply people were committed to maintaining traditional beliefs, even when evidence suggested problems. The Church's power extended beyond education into politics and daily life. Religious leaders influenced kings and governments, and their judgments could shape entire societies. Being accused of heresy was not a minor matter. It could lead to imprisonment, social ruin, or worse. This made scholars extremely cautious. Even if someone privately doubted accepted ideas, publicly expressing those doubts required immense courage. However, by the late Middle Ages and early Renaissance, small cracks began to appear in this rigid system. The Renaissance encouraged renewed interest in learning, mathematics, and observation. The invention of the printing press allowed ideas to spread more widely than before. Explorers discovered new lands that challenged traditional maps and assumptions about the world. Yet, despite these changes, church-backed science still dominated official thinking, and ancient authorities remained largely unquestioned. It was into this world that Galileo would eventually introduce a radically different approach. Before him, science was not about testing nature directly, but about interpreting old texts. Before him, the universe was seen as fixed, perfect, and centered on humanity. And before him, the Church stood as the guardian of both spiritual and scientific truth. Understanding this background makes Galileo's rebellion all the more significant. He was not merely arguing about planets and stars. He was challenging a system that had controlled knowledge for centuries. His insistence on observation, experimentation, and mathematics threatened the very foundation of church-backed science. In a world where authority defined truth, Galileo dared to suggest that nature itself should be the final judge. Galileo Galilei's early life played a crucial role in shaping the scientist he would later become. Long before his conflict with the Church or his revolutionary astronomical discoveries, Galileo was already developing a deep curiosity about nature, motion, and the laws that governed the physical world. His childhood, education, and early experiences exposed him to music, mathematics, philosophy, and careful observation, all of which combined to form a mindset that questioned tradition and sought truth through evidence. Galileo was born on February 15, 1564, in Pisa, a city in what is now Italy. He came from a modest but intellectually active family. His father, Vincenzo Galilei, was a well-known musician, music theorist, and mathematician. Vincenzo was not only skilled in music, but also critical of blindly accepting ancient authorities. He often challenged traditional musical theories using experimentation and mathematical reasoning. Growing up in such an environment, Galileo was exposed early to the idea that knowledge should be tested rather than simply accepted. This influence from his father quietly planted the seeds of Galileo's later scientific approach. As a child, Galileo showed signs of exceptional intelligence and curiosity. He was fascinated by how things worked and enjoyed solving problems. His early education was broad and included literature, logic, and philosophy, but mathematics soon captured his attention. Initially, Galileo was expected to pursue a practical and respectable career, and his father encouraged him to study medicine. At the age of 17, Galileo enrolled at the University of Pisa as a medical student. However, medicine did not truly interest him. Instead, he found himself drawn to mathematics, geometry, and physics. subjects that allowed him to explore patterns and principles underlying the natural world. One of the most famous stories from Galileo's student years illustrates his early curiosity about motion and time. While attending church services in Pisa, he noticed a large lamp swinging back and forth from the ceiling. He observed that the time it took for the lamp to complete each swing remained nearly constant, even as the swings became smaller. Using his own pulse to measure time, Galileo realized that the period of the pendulum did not depend on the size of its swing. This simple but powerful observation later became essential to the development of pendulum clocks. More importantly, it revealed Galileo's habit of observing everyday phenomena closely and asking deeper questions about them. Galileo eventually left the University of Pisa without completing his medical degree, choosing instead to pursue mathematics independently. This decision disappointed his father, but Galileo was determined. He studied the works of ancient mathematicians such as Euclid and Archimedes, the latter becoming a particularly strong influence. Unlike Aristotle, whose ideas dominated medieval education, Archimedes emphasized mathematics and logical reasoning. Galileo admired this approach and adopted it as a model for his own thinking. In 1589, Galileo was appointed as a lecturer in mathematics at the University of Pisa. During this period, he began to openly question Aristotle's teachings on motion. Aristotle claimed that heavier objects fall faster than lighter ones, and that an object's natural state was rest. Galileo doubted these ideas, not because he wanted to be rebellious, but because they did not align with observation. According to later accounts, Galileo conducted experiments by dropping objects of different weights from the Leaning Tower of Pisa to show that they fell at nearly the same rate. Whether or not this specific event happened exactly as described, it reflects the kind of experimental thinking Galileo was developing. Galileo's curiosity about motion went beyond falling objects. He wanted to understand why things moved the way they did and what laws governed that movement. He studied inclined planes, rolling balls down slopes to slow motion enough to measure it accurately. Through these experiments, he discovered relationships between distance, time, and speed. These studies laid the groundwork for the concept of acceleration and directly challenged Aristotle's view that motion required a continuous force. In 1592, Galileo moved to the University of Padua, where he spent nearly 18 years. This period was one of the most productive and formative of his life. Padua was under Venetian rule, which allowed more intellectual freedom than many other regions of Italy. Here, Galileo taught mathematics, mechanics, and astronomy, and his curiosity flourished. He designed scientific instruments, including improved compasses and measuring devices, and gained a reputation as an innovative thinker and inspiring teacher. Galileo's fascination with nature was not limited to motion alone. He was deeply interested in how mathematics could describe the physical world. He believed that nature followed precise laws that could be expressed through numbers and geometry. This belief marked a major shift away from purely philosophical explanations of nature. For Galileo, understanding the universe meant measuring it, testing it, and expressing its behavior mathematically. Throughout his early life, Galileo showed a willingness to challenge accepted ideas, but he was not reckless. His skepticism was rooted in careful observation and reasoning. He did not reject tradition simply to oppose it. He rejected it when it failed to match reality. This balance of curiosity, discipline, and courage defined his approach to science. By the time Galileo turned his attention to astronomy and the heavens, his intellectual foundation was already firmly established. His curiosity about nature and motion had taught him to trust observation over authority and experimentation over tradition. These qualities would soon lead him to discoveries that transformed humanity's understanding of the universe and brought him into conflict with powerful institutions. In many ways, Galileo's early life shows that great scientific revolutions do not begin suddenly. They grow slowly, shaped by family influences, education, simple observations, and an unrelenting desire to understand how the world truly works. Galileo's curiosity about nature and motion was not just the beginning of his career. It was the driving force behind a new way of thinking that would forever change science. The turning point in Galileo Galilei's life, and in the history of science itself, came with the telescope and the discoveries it revealed. Before Galileo, the heavens were believed to be perfect, unchanging, and fundamentally different from the earth. Ancient philosophers, especially Aristotle, taught that everything above the moon was flawless and eternal, while Earth was imperfect and constantly changing. These ideas had dominated human thought for nearly 2,000 years and were strongly supported by the Church. When Galileo turned the telescope toward the sky, he did not just discover new objects. He shattered an entire world, that humanity had trusted for centuries. The telescope was not originally Galileo's invention. In 1608, news reached Italy of a device developed in the Netherlands that could make distant objects appear closer. Galileo immediately recognized its potential. Using his knowledge of optics and mathematics, he built his own improved version of the telescope in 1609. While early telescopes magnified objects only a few times, Galileo's versions were far more powerful, allowing him to observe the heavens in unprecedented detail. What made Galileo truly revolutionary was not the instrument itself, but how he used it, to investigate the universe rather than for military or commercial purposes. When Galileo first aimed his telescope at the moon, what he saw directly contradicted ancient beliefs. According to Aristotle, the moon was a smooth, perfect sphere. Galileo, however, observed mountains, valleys, and craters on its surface. By studying how light and shadow behaved on the moon, he even estimated the heights of its mountains. This was a shocking discovery. If the moon had an uneven, Earth-like surface, then the idea of a perfect, unchanging heavenly realm was false. The boundary between the heavens and the earth, so central to ancient philosophy, suddenly began to collapse. Galileo's observations did not stop there. When he turned his telescope toward the night sky, he noticed that the Milky Way was not a smooth band of light, as previously believed, but a vast collection of countless individual stars. This discovery expanded the known size of the universe and suggested that Earth occupied a far less central and special position than people had assumed. The heavens were not simple or limited. They were immense and complex beyond imagination. One of Galileo's most important discoveries came in January 1610, when he observed 4 small objects orbiting the planet Jupiter. Over several nights, he carefully recorded their movements and realized that they were moons circling Jupiter. This finding dealt a major blow to the Earth-centered model of the universe. For centuries, it had been assumed that all celestial bodies revolved around Earth. Yet here was clear evidence that some objects orbited another planet. This meant Earth was not the unique center of all motion in the universe, and it opened the door to alternative models of cosmic structure. Galileo's observations of Venus provided even stronger evidence against the ancient geocentric system. He noticed that Venus went through a complete set of phases, similar to the phases of the Moon. This could only be explained if Venus orbited the Sun rather than Earth. The Earth-centered model could not account for this behavior without extreme and unnatural adjustments. In contrast, the Sun-centered model proposed earlier by Copernicus explained the phases of Venus naturally and simply. Although Copernicus had suggested this model decades earlier, it was Galileo's telescope that finally provided strong observational support for it. Another revolutionary discovery came from Galileo's study of the Sun. Using careful methods to protect his eyes, he observed dark spots moving across the Sun's surface. These sunspots appeared, changed shape, and disappeared over time. This directly contradicted the belief that the Sun was a perfect, unblemished sphere. Moreover, the movement of sunspots suggested that the Sun itself rotated, revealing that change and motion existed even in the highest regions of the heavens. Each of these discoveries challenged ancient beliefs not just individually, but collectively. Together, they destroyed the idea of a perfect and unchanging universe and replaced it with one that was dynamic, imperfect, and governed by natural laws. Galileo's observations showed that the same physical principles applied to both Earth and the heavens, uniting the universe under a single framework of understanding. This was a radical departure from the old world that separated earthly physics from celestial perfection. The reaction to Galileo's discoveries was mixed. Some scholars were fascinated and excited, while others refused to look through the telescope at all. Many critics claimed that the telescope was unreliable or that Galileo's observations were illusions. Others argued that even if the observations were correct, they should not be taken seriously if they contradicted ancient authorities or religious interpretations. This resistance highlighted how deeply rooted traditional beliefs were, and how threatening Galileo's discoveries seemed to established power structures. Galileo published his findings in 1610 in a book that quickly gained attention across Europe. He wrote in clear language rather than obscure academic Latin, making his ideas accessible to a wider audience. This further alarmed church officials, who feared that such ideas would spread beyond scholarly circles and challenge religious authority. What began as astronomical observation soon became a cultural and theological conflict. The telescope, in Galileo's hands, became more than a scientific instrument. It became a symbol of a new way of knowing, one based on observation, evidence, and reason rather than tradition alone. Galileo's discoveries did not merely add new facts to human knowledge. They forced humanity to rethink its place in the universe. Earth was no longer the immovable center of creation. The heavens were no longer perfect and beyond change. Instead, the universe was revealed as vast, complex, and governed by laws that humans could discover through careful study. In challenging ancient beliefs, Galileo transformed science forever. His work marked the beginning of modern astronomy and played a central role in the scientific revolution. The telescope opened humanity's eyes to a new universe, and Galileo had the courage to trust what he saw, even when it contradicted centuries of accepted wisdom. The conflict between Galileo Galilei and the Catholic Church was not a sudden clash, but a slow, escalating struggle between two different ways of understanding truth. By the early 17th century, Galileo's scientific discoveries had begun to challenge long-standing beliefs about the universe that were deeply connected to religious authority. The trial of 1633 became the dramatic climax of this conflict, symbolizing the tension between emerging scientific inquiry and established religious doctrine. At the heart of the disagreement was the question of the structure of the universe. For centuries, the Church had supported the Earth-centered or geocentric model based on the teachings of Aristotle and Ptolemy. This model aligned with certain interpretations of the Bible, which described the Earth as fixed and immovable. While the Church did not oppose science itself, it expected scientific ideas to remain consistent with Scripture as interpreted by religious authorities. Any idea that appeared to contradict these interpretations was viewed with suspicion. Galileo's telescopic discoveries strongly supported the Sun-centered or heliocentric model originally proposed by Nicolaus Copernicus. Observations such as the moons of Jupiter and the phases of Venus made it increasingly difficult to defend the geocentric system. Galileo believed that these findings revealed how the universe truly worked, and that Scripture should be reinterpreted when clear evidence from nature contradicted traditional readings. This view, however, was highly controversial. Church leaders feared that allowing individuals to reinterpret Scripture based on scientific evidence could weaken religious authority and lead to widespread doubt. Initially, Galileo was not officially condemned. In 1616, Church authorities declared heliocentrism to be formally heretical because it appeared to contradict the Bible. Galileo was summoned and warned not to hold or defend the Sun-centered theory as fact. He was allowed to discuss it only as a mathematical hypothesis, not as a true description of reality. For several years, Galileo complied publicly with this restriction, focusing on other scientific work and avoiding direct confrontation. The situation changed in the late 1620s when Galileo believed the political and religious climate had become more favorable. A new pope, Urban Roman VIII, had been elected, and he was someone Galileo knew personally. Encouraged by this relationship, Galileo decided to write a major work comparing the geocentric and heliocentric systems. In 1632, he published a book written as a dialogue between three characters discussing the two models of the universe. Although Galileo claimed neutrality, the arguments in favor of the Sun-centered system were far more convincing, while the defense of the Earth-centered view appeared weak and simplistic. This book quickly drew attention and controversy. Many church officials felt that Galileo had violated the warning given to him in 1616. Worse still, some believed that one of the dialogue's characters resembled the Pope himself and made him appear foolish. Whether or not this was Galileo's intention, the book was seen as a challenge to church authority. As a result, Galileo was ordered to travel to Rome to face the Inquisition. In 1633, at the age of nearly 70, Galileo stood trial before the Roman Inquisition. The trial focused on whether he had disobeyed the Church, his earlier command, by defending heliocentrism as truth. Galileo argued that his book merely presented a discussion, and that he had not explicitly stated heliocentrism as fact. However, the Inquisition produced documents suggesting that Galileo had been clearly instructed not to promote the theory in any form. Faced with these accusations, Galileo found himself in a powerless position. The trial was not a scientific debate in the modern sense. The Church was not weighing evidence from observation and experimentation. Instead, it was enforcing obedience to religious authority. Galileo's scientific arguments, no matter how strong, were secondary to the issue of whether he had defied church orders. Under threat of severe punishment, Galileo was pressured to confess that he had been wrong. Eventually, Galileo was found vehemently suspect of heresy. He was forced to publicly renounce his support for the centered universe. This moment remains one of the most symbolic events in the history of science. A man who had dedicated his life to discovering truth through observation was compelled to deny what he knew to be supported by evidence. According to popular legend, after recanting, Galileo quietly said, "And yet it moves," referring to the Earth's motion, though there is no solid historical proof of this statement. As punishment, Galileo was sentenced to house arrest for the remainder of his life. His book was banned, and he was forbidden from discussing heliocentrism. Confined to his home, first near Rome and later in Florence, Galileo lived under constant supervision. Despite these restrictions, he continued to work privately. During this period, he wrote one of his most important scientific works on motion and mechanics, which would later influence Isaac Newton and the development of classical physics. The trial of 1633 had lasting consequences beyond Galileo's personal suffering. It sent a powerful message to scholars across Europe about the dangers of challenging established authority. For many years, the Church's condemnation slowed the acceptance of heliocentrism, even as evidence in its favor continued to grow. At the same time, the trial became a symbol of the struggle between free inquiry and institutional control. In the long run, history judged Galileo differently from his judges. As scientific knowledge advanced, the sun-centered model became universally accepted. Centuries later, the Church formally acknowledged that Galileo had been wronged. In 1992, after a long review, the Vatican admitted errors in the way the case had been handled. The conflict between Galileo and the Church was not simply about astronomy. It was about who had the authority to define truth. Galileo's trial showed how threatening new ideas can be to established systems of power. His experience remains a powerful reminder that progress often comes at a great personal cost, and that the pursuit of truth can challenge even the most deeply rooted beliefs. Galileo Galilei's courage, recantation, and house arrest represent one of the most powerful and human chapters in the history of science. This period of his life shows not only the strength of his intellect, but also the emotional and moral struggle of a man caught between truth and survival. Galileo was not a reckless rebel seeking conflict. He was a devoted scientist who believed deeply in what observation and reason revealed about the universe. Yet when faced with overwhelming authority and the threat of severe punishment, he was forced into a painful compromise that defined his final years. Galileo's courage was evident long before his trial. At a time when most scholars relied on ancient texts, he trusted direct observation. After using the telescope to uncover evidence supporting the sun-centered universe, Galileo chose to publish and defend his findings despite knowing the risks. He was fully aware that the Church had already declared heliocentrism dangerous and contrary to Scripture. Still, Galileo believed that truth discovered through nature could not contradict divine creation. For him, studying the universe was a way of understanding God's work more deeply, not challenging faith itself. What made Galileo's courage especially remarkable was the world he lived in. The Catholic Church was not only a religious institution, but also a powerful political force. To oppose its teachings publicly could lead to loss of freedom, reputation, or even life. Many scientists who privately agreed with Galileo remained silent. Galileo, however, continued to write, teach, and argue that evidence mattered. His confidence came from years of careful observation and mathematical reasoning. He believed that once people saw the evidence, they would accept the truth. This courage eventually led him to a point of no return. After the publication of his book comparing the Earth-centered and sun-centered models, Galileo was summoned to Rome. By then, he was nearly 70 years old, physically weak, and suffering from illness. Despite this, he made the difficult journey, knowing the outcome could be devastating. Facing the Inquisition required immense bravery. Even though Galileo hoped his reputation and past obedience might protect him. During the trial, Galileo found himself trapped. The Church was not interested in debating scientific evidence. The issue was obedience. Documents were presented claiming that Galileo had been explicitly forbidden from defending heliocentrism in any form. Whether or not Galileo fully understood the limits imposed on him years earlier mattered little. The authority of the Church outweighed his explanations. The pressure was intense, and the consequences of resistance were terrifying. Galileo's recantation was the most painful moment of his life. Standing before church officials, he was forced to publicly deny the idea that Earth moves around the sun. For a man who had devoted decades to uncovering truth through observation, this was a profound humiliation. His words of denial were not a reflection of his beliefs, but a response to fear, exhaustion, and the reality of his situation. He was old, alone, and facing an institution that held absolute power over his fate. Some later critics have questioned Galileo's decision to recant, suggesting that true courage would have meant refusing at any cost. However, such judgments often ignore the human reality of his situation. Galileo was not only risking his own life, but also considering the suffering that harsher punishment would bring. By recanting, he preserved his life and, indirectly, his ability to continue working in some form. His decision was not cowardice, but survival. After the trial, Galileo was sentenced to house arrest for the rest of his life. His book was banned, and he was forbidden from teaching or discussing heliocentrism. At first, he stayed in Rome under strict supervision before being allowed to return to his home near Florence. Although spared imprisonment, his freedom was severely limited. He could not travel freely, meet openly with students, or publish his ideas. For a man who thrived on intellectual exchange, this isolation was deeply painful. House arrest, however, did not break Galileo's spirit. Despite declining health and growing blindness, he continued to think, write, and explore scientific questions. Confined to his home, he focused on mechanics and motion, areas less directly connected to astronomy. During this time, he completed a major work on motion and the laws governing it. This book, written in secret and published abroad, would later become foundational to classical physics and strongly influence scientists like Isaac Newton. Galileo's life under house arrest reveals a quieter, deeper form of courage. Stripped of public voice and recognition, he remained faithful to his commitment to truth. Even when silenced, his ideas continued to move forward. His work spread beyond Italy, inspiring thinkers across Europe. In this way, the attempt to suppress his ideas ultimately failed. The story of Galileo's recantation and house arrest also exposes the limits of authority. The Church succeeded in forcing one man to publicly deny a truth, but it could not stop the progress of knowledge. Over time, evidence in favor of heliocentrism became overwhelming. What Galileo was forced to deny in words became undeniable in reality. Galileo died in 1642, still officially condemned and confined, never seeing his ideas fully accepted. Yet history transformed his apparent defeat into a lasting victory. Centuries later, the Church acknowledged its error, and Galileo came to symbolize the triumph of reason and evidence over enforced belief. His courage was not only in speaking out, but in enduring silence. His recantation was not the end of his legacy, but a reminder of the human cost of progress. And his house arrest, intended to isolate and suppress him, became the setting for some of his most enduring contributions to science. Galileo's story teaches us that truth may be delayed, challenged, and even denied, but it cannot be permanently silenced. The scientific method and Galileo Galilei's lasting influence are inseparable. Galileo did not simply make important discoveries. He transformed the very way humans seek knowledge about the natural world. Before his time, science was largely shaped by ancient authority, philosophical speculation, and religious tradition. After Galileo, science increasingly became a disciplined process based on observation, experimentation, measurement, and mathematical reasoning. His approach laid the foundation for modern science and continues to shape how knowledge is created today. Before Galileo, the study of nature was known as natural philosophy. Scholars relied heavily on the writings of thinkers like Aristotle, whose ideas were treated as unquestionable truths. If a claim came from a respected ancient authority, it was often accepted without direct testing. Observation existed, but it was secondary to interpretation of texts. Galileo challenged this approach by insisting that nature itself should be the ultimate authority. He believed that to understand the universe, one must look at it carefully, test ideas against reality, and be willing to abandon old beliefs when evidence contradicted them. At the heart of Galileo's scientific method was observation. He carefully studied natural phenomena, from the motion of falling objects to the movement of planets. Unlike many scholars before him, he trusted what he saw and measured rather than what tradition claimed. His use of the telescope is a perfect example. Instead of dismissing new observations because they conflicted with established ideas, Galileo accepted them as clues to deeper truths about the universe. Experimentation was another crucial element of Galileo's method. He did not merely observe nature passively. He designed experiments to isolate variables and test specific questions. His studies of motion, such as rolling balls down inclined planes, allowed him to slow down movement and measure time and distance accurately. This experimental approach helped him discover laws governing acceleration and motion, challenging long-held beliefs about how objects move. Through experimentation, Galileo showed that physical laws could be discovered through careful testing, rather than philosophical argument alone. Measurement and mathematics played a central role in Galileo's thinking. He believed that the universe was written in the language of mathematics, and that understanding nature required precise measurement and mathematical description. This was a radical shift from earlier approaches that relied on qualitative explanations. By expressing natural laws mathematically, Galileo made them universal and predictive. His work demonstrated that nature follows consistent rules that can be described, tested, and applied. Another key aspect of Galileo's scientific method was skepticism toward authority. He respected ancient thinkers but refused to accept their ideas without evidence. This did not mean rejecting tradition entirely. It meant treating it as a starting point rather than a final answer. Galileo's willingness to question accepted knowledge encouraged a culture of inquiry and debate. This attitude became a defining feature of modern science. Galileo also emphasized the importance of repeatability and transparency. He carefully recorded his observations and methods so others could examine and verify them. By publishing his findings and explaining how he reached his conclusions, he invited scrutiny and discussion. This openness allowed scientific knowledge to grow collectively rather than remaining hidden or reserved for a select few. Galileo's lasting influence can be seen in the work of later scientists who built upon his methods and discoveries. Isaac Newton, one of the greatest scientists in history, openly acknowledged Galileo's influence. Newton's laws of motion and universal gravitation expanded on Galileo's studies of motion and mechanics. Without Galileo's experimental and mathematical groundwork, Newton's achievements would have been impossible. Beyond individual scientists, Galileo's influence reshaped entire scientific disciplines. Astronomy, physics, and engineering all evolved through the application of the scientific method he championed. His insistence that the same physical laws apply both on Earth and in the heavens unified the universe under a single framework of understanding. This idea remains central to modern physics. Galileo's impact extended beyond science into culture and philosophy. His conflict with the Church highlighted the importance of intellectual freedom and the right to question authority. Although he was condemned during his lifetime, his ideas ultimately triumphed, reinforcing the principle that truth is discovered through evidence rather than enforced belief. This lesson influenced later movements that valued reason, inquiry, and individual thought. Education also changed as a result of Galileo's legacy. Over time, experimental science replaced purely text-based learning in universities. Laboratories, experiments, and empirical research became central to scientific education. Students were encouraged to observe, test, and question rather than memorize accepted doctrines. This transformation can be traced directly to the methods Galileo practiced and promoted. Today, the scientific method is used in countless fields, from medicine and technology to environmental science and space exploration. While the method has evolved and become more refined, its core principles observation, experimentation, measurement, and critical thinking remain deeply rooted in Galileo's work. Every modern scientific discovery carries traces of his approach. Galileo's lasting influence lies not only in what he discovered, but in how he discovered it. He showed humanity that understanding the universe requires humility before evidence and courage to follow truth wherever it leads. His methods turned science into a dynamic, self-correcting process rather than a fixed collection of beliefs. In doing so, Galileo helped launch a scientific revolution that continues to shape the modern world, making him one of the most influential figures in the history of human thought. Galileo Galilei's legacy in modern science and free thought is one of the most profound and enduring in human history. Although he lived in the 16th and 17th centuries, the impact of his ideas reaches deeply into the modern world. Galileo was not only a brilliant scientist, he was a symbol of intellectual courage, rational inquiry, and the belief that truth should be discovered through evidence rather than imposed by authority. His legacy reshaped science, transformed human understanding of the universe, and helped establish the principle of free thought that remains essential to modern societies. In modern science, Galileo is often remembered as one of the founders of experimental physics and modern astronomy. Before him, science relied heavily on ancient texts and philosophical reasoning. Galileo changed this by insisting that nature must be studied directly. He believed that observation, experimentation, and measurement were the keys to understanding reality. This approach became the foundation of the scientific method, which continues to guide scientific research today. Every time a scientist tests a hypothesis, measures results, and revises conclusions based on evidence, Galileo's influence is present. Galileo's work helped establish the idea that the universe operates according to universal laws. He demonstrated that the same physical principles apply both on Earth and in the heavens. This was a revolutionary idea at a time when people believed the sky followed different rules than the Earth. Modern physics, astronomy, and engineering all rely on this assumption of universal laws. From understanding planetary motion to designing satellites and space missions, Galileo's way of thinking remains central to scientific progress. His influence can be clearly seen in later scientific giants. Isaac Newton built upon Galileo's studies of motion to develop the laws of motion and universal gravitation. Albert Einstein admired Galileo's emphasis on observation and experimentation, calling him the father of modern science. In this way, Galileo stands at the beginning of a chain of discovery that leads directly to modern science and technology. Beyond scientific methods and discoveries, Galileo's legacy is deeply tied to free thought. His life demonstrated the importance of intellectual independence and the courage to question established beliefs. Galileo lived in a world where religious and philosophical authorities claimed control over truth. By challenging these authorities with evidence, he showed that ideas must be open to questioning and revision. This principle lies at the heart of free thought and democratic societies. Galileo's conflict with the Church became a powerful historical lesson about the dangers of suppressing ideas. Although he was forced to recant and live under house arrest, his ideas could not be contained. Over time, evidence supported his views, and the world came to accept the sun-centered universe. This outcome reinforced the belief that truth cannot be permanently silenced by authority. Today, Galileo's story is often cited as a reminder of why freedom of inquiry and expression are essential for progress. In education, Galileo's legacy transformed how knowledge is taught and learned. Modern science education emphasizes experimentation, critical thinking, and questioning rather than memorization of accepted facts. Students are encouraged to test ideas, analyze data, and challenge assumptions. This educational philosophy reflects Galileo's belief that understanding comes from direct engagement with the world, not passive acceptance of tradition. Galileo's influence also extends into philosophy and ethics. His insistence that observation should guide belief helped shape modern rationalism and empiricism. Philosophers after Galileo increasingly argued that knowledge should be grounded in experience and reason. This shift played a key role in the Enlightenment, a movement that promoted reason, individual rights, and skepticism of absolute authority. The political and social freedoms enjoyed in many parts of the world today are connected, in part, to this intellectual transformation. In modern society, Galileo's legacy can be seen in the way science interacts with power. His life serves as a reminder that scientific truth should not be determined by political, religious, or social pressure. Scientific institutions today emphasize peer review, transparency, and independence precisely to avoid the kind of authority-based suppression Galileo faced. While conflicts between science and authority still occur, Galileo's example strengthens the argument for protecting scientific freedom. Galileo's legacy also inspires those who challenge accepted ideas in other fields. Innovators, thinkers, and reformers often see him as a model for standing by evidence even when it is unpopular. His life shows that progress often begins with uncomfortable questions and resistance from established systems. This lesson applies not only to science, but also to social reform, education, and human rights. Importantly, Galileo's legacy reminds us that scientists are human. He experienced fear, doubt, and compromise, yet his ideas survived and reshaped the world. This human aspect makes his legacy more powerful. It shows that advancing knowledge does not require perfection, but persistence, honesty, and commitment to truth. Today, Galileo is honored not only with monuments and textbooks, but with the continued use of the methods and values he championed. Spacecraft, telescopes, and scientific institutions bear his name, symbolizing humanity's ongoing quest to understand the universe. More importantly, his legacy lives in the idea that no belief is beyond question, and no authority is above evidence. In modern science and free thought, Galileo represents the triumph of reason over tradition, inquiry over obedience, and evidence over assumption. His life and work helped humanity move from a closed, authority-driven world view to an open, evidence-based understanding of reality. For this reason, Galileo Galilei remains not just a historical figure, but a lasting symbol of intellectual freedom and scientific truth.